Hello, great friends. Your physics companion is here to bring you another episode of Learning Physics. IBM is my name, and I would like to take you to waves and superposition. This is going to be part two of these solved past paper questions, specifically multiple choice. Do not hesitate to download the documents. The documents the links to the documents are attached in the video description, where you can download these multi-paper choice questions. It is entirely free, and you can practice on these multiple choice questions. In part one, I mentioned that waves and electricity, waves and superposition together with electricity will contribute about 20% of, not 20%, that is 20, almost 20 out of 40 multiple choice questions. Therefore, it will be good to spend much time practicing waves and gaining the concepts behind waves. Don't forget to subscribe, share the videos with your friends just for learning purposes, and I hope you learn something from this. Let's go to part two of superposition and waves. This is solved past paper question. So in part one, I think we stopped on page 20, and in part two, I want us to start from page 21. Okay. The diagrams show the diffraction of water waves in a ripple tank as they pass through a gap between two barriers. Which diagram is correct? So let's check the diagrams. We know that diffraction is maximum when the wavelength is approximately the same as the size of the gap. Diffraction is maximum when the wavelength is approximately equal to the size of the gap. So the question is which diagram is correct? So when we check the wavelength here, compare with the size, the diffraction, the wavelength has not changed. Of course, the wavelength does not change due to diffraction. It is just the angle of diffraction that changes. Here we are seeing that the wavelength has become smaller, which is practically not true. Here we are seeing that the wavelength has become bigger in comparison to this part here, which is also not possible. Similarly, here we see that the wavelength has decreased compared to this one here. Remember, the wavelength is the distance between the two successive wavefronts. So it means the answer is going to be B, because in B we see that the wavelength has remained the same. The wavelength does not change when diffraction occurs. So the answer is going to be B. A beam of light from a laser is incident normally on a double slit. Interference fringes are seen on a screen placed parallel to the double slit. The separation of the two slits is A. The distance between the slits and the screen is D. The distance between the centers of two adjacent bright fringes is X. That means we can come up with a formula. Wavelength is equal to A times X divided by D, because it is a double slit. D and A are both halved. So we see that lambda times D is equal to A times X. They're saying D and A are both halved. What is the distance between the centers of two adjacent bright fringes after these changes? So maybe to use simple mathematics, let the initial distance be X, when the first distance between the slit and the screen is D and the slit separation is A. Then when D is halved and A is halved, what is the new value of X? So let this be, let's the first value of X be equal to lambda times D over A. Let this be X1, and I'm calling this one just X. Then the second value of X is going to be lambda. D is halved, so we shall have a half of D. And A is halved, so we shall have a half of A. So a half still cancels. And this still takes us back to lambda D over A, which is the same as X. So the distance remains X. It is the same, because D is directly proportional to A. When D is halved and A is also halved, it means there is no change in X. A beam of light of wavelength 400 nanometers is incident normal on a diffraction grating that has 300 lines per millimeter. Lines per millimeter. The light passes through the grating and produces a series of maximum which are observed on a semicircular screen as shown here. What is the total number of maxima observed on the screen? So number of maxima, we know that for a diffraction grating, n lambda is equal to d sine of theta. N is maximum when sine theta is equal to 1. That means when theta is 90 degrees. So it means n maximum is going to be d divided by lambda times 1, of course. But remember, there will be a central bright fringe there, which corresponds to n equals to 0, and will be n maximum that side and n maximum the other side because they are symmetrical around the center. There will be n maximum that side and n maximum this side, then plus 1, which corresponds to n equals to 0. So it means the answer must be an odd number, that is 1. Okay, so let's find n first. Before we find n, we have the number of lines is in 1 millimeter, there are 300 lines. Then how about in 1 meter? Remember 1 millimeter is 1 over 1,000 meters. So in 1 over 1,000 meters, there are 300 lines, which means 1 meter will have 300 times 1,000 lines. So the number of lines per meter is 300,000 lines. Therefore, you also know that D is equal to 1 over N, where N is the number of lines per meter. So D is going to be 1 over N. So I'm now substituting here. So N maximum is going to be D, which is 1 over N. This is 1 over 300,000, of course, times 1, divided by wavelength, which wavelength is given as 400 nanometers. So that is 400 times 10 to the power negative 7. So this is going to be 1 divided by 300,000 times 400 exponent negative 7. No, negative 9 nano opposite exponent negative 9 because it's nano, which gives us 8.33. But I said we round off to a whole number, but we round off to the smallest whole number, not to the next whole number. Even if it was 8.7 or 8.99, we would still round off to 8. So this is going to be 8. So this is going to be n equals to 8 down and n equals to 8 up. So we have 8 plus 8, that is above and below, then plus 1, which is at the center, which makes it 17. So our answer is going to be D. A wire is stretched by applying increasing values of force F. For each value of force applied, the extension X is recorded. A force extension graph is plotted from the data obtained. Which statement about the area under the graph must be correct? This question must be just misplaced, but we shall still answer it. It is not in waves, it is in Young modulus. So which statement about the area under the graph must be correct? So this is under deformation of solids. It is a graph of force against extension. So the area under the graph is equal to a half F times X, which is actually the area would be a half Fx, which would be because the force was increasing, for each value of force applied, the extension X is recorded. This will be the elastic potential energy, or the energy stored in the stretched material. But the question is, which statement about the area under the graph must be correct? It can be calculated as a half Fx. It is the elastic potential energy stored in the stretched sample. It is the work done in stretching the sample. It would be the same for any wire for the same material. So this one is obviously wrong. Let's go back. A wire is stretched by applying increasing values of F. So F is not the maximum, but they are increasing. It could go beyond the elastic limit. Therefore, we can ignore this. We may not calculate the area from a half Fx because it could go beyond and the material may undergo elastic and plastic deformation. But all we are very sure of is that whether it undergoes elastic or plastic deformation, the area under the graph is going to be the work done in stretching the sample to whatever point we stretch. Therefore, the most appropriate answer to this question is going to be C. If they had told us that force was directly proportional to extension throughout, then we would know that the area is a half Fx. If they had told us Hooke's law is obeyed throughout, then we could also still think that elastic potential energy stored in the stretched sample is the area under the graph. But since such conditions have not been mentioned here, then we can agree that the area under the graph simply represents the work done in stretching the material to whatever point, whether it undergoes elastic deformation or plastic deformation before it breaks. The work done in stretching is the area under the graph. A progressive radio wave in a vacuum has a frequency of 75 megahertz. What is the phase difference between 2 points on the wave that are 50 centimeters apart from each other? What is the phase difference? So it has this, it has that frequency. It is a progressive radio wave in a vacuum, has frequency 75 hertz. So let's find the wavelength first. So wavelength is going to be V over F. It is a progressive radio wave which travels at the speed of light, 3 times 10 power 8. The frequency is 75 times 10 power 6. So that is going to give us the wavelength, 3 exponent 8 divided by 75 exponent 6. So the wavelength is going to be 4. The wavelength is 4 meters. Then what is the phase difference between 2 points on the wave that are in phase 50 centimeters apart? So 4 meters is the same as 400 centimeters. So we know that phase difference is going to be 360 degrees into x, that is the distance out of step or distance apart, divided by the wavelength. So this is going to be 360, distance apart is 50 centimeters, divided by wavelength, which is 400 centimeters. So we have 50 divided by 400, then times 360, which gives us 45 degrees. So theta is 45 degrees. So the answer is going to be B. Which statement is correct for longitudinal waves but not correct for transverse waves? We know longitudinal waves, particles vibrate perpendicular to the direction of propagation of the wave. And longitudinal waves, particles vibrate parallel. For transverse, particles vibrate perpendicular to the direction of propagation of the wave. But all waves, whether longitudinal or transverse, can form stationary waves. Not all waves can travel through a vacuum. Not all waves can travel through a vacuum, but all waves can travel through a given medium, whether it is transverse or longitudinal. Although for transverse specifically, electromagnetic waves do not travel through, can travel through a vacuum. Yet other types of transverse waves may not travel through a vacuum. Just like longitudinal wave, sound cannot travel through a vacuum, but they can only travel through a medium because they must transfer energy. Which statement is correct for longitudinal waves but not correct for transverse waves? They can only travel through a medium. So longitudinal waves can only travel through a medium. Think about sound waves. They cannot go through a vacuum. Therefore, the most appropriate answer is going to be this. So this one is wrong. They can transfer energy in the direction of travel. Both longitudinal and transverse can transfer energy. They consist of peaks and troughs. Both consist of peaks and troughs. However, longitudinal waves can only travel through a medium. Transverse waves, like electromagnetic waves, can travel through a vacuum, unlike sound waves, which may not travel through a vacuum. They need a medium for their propagation. So the answer here is going to be B. That means C is wrong and D is also wrong. A loudspeaker emitting a sound wave of wavelength, of a single frequency is placed at distance L from a reflecting source as shown there. A stationary wave is formed with an antinode at the loudspeaker. A microphone is moved from the loudspeaker to the reflector. Before the microphone reaches the reflector, it takes 4 points where the sound intensity is minimum. So it means between the loudspeaker and before we reach the reflector, we should have 4 nodes. So let me say this is going to be one node. Let me put here one node, second node. I will put here the third node, the fourth node. That means automatically I need there will be fifth node just at the reflector. So if there's an antinode at the loudspeaker, I will sketch this. This is just a sketch to give us a picture of what is happening here. So there are 1, 2, 3, 4 nodes before the reflector. So I've added the fifth node just at the reflector because we don't expect an antinode at the reflector. It must be a node. So what is the wavelength of the sound wave? So the length L has, this is a half a cycle, that is one cycle, 1.5, 2 cycles, and a quarter. So the length L is representing 2 cycles and a quarter of the wavelength, which means the length is representing, that is going to be 4 times 2 plus 1, that is 9/4 of wavelength. So the question is, what is the wavelength of the sound? So wavelength is going to be, we take the 4 up, so it becomes 4L divided by 9, which makes our answer to be C. A source of sound of frequency F at point Z is moving at a steady speed. The pattern of the emitted wavefronts is shown here. Before reading even the questions, you see that the source is placed at Z. So it means at X, the frequency must be increasing because the wavelength is decreasing. Frequency is inversely proportional to wavelength. We see that the wavefronts are getting closer. So towards X, the frequency is increasing. And towards Y, we see that the wavelength is increasing because the wavefronts are moving apart. It means the frequency is decreasing. So which law describes the frequencies of the sound heard by a stationary observer at X and at Y? So at X it should be higher than F, and at Y should be less than F. So let's see. X less than, that is not true. X less than, that is not true. X should be greater, so we remain with the C and D. Then F towards Y, it should be less. So the answer is going to be C. Towards X, it is greater than F. Towards Y, it is less than F. What is not a possible value of the wavelength of the named electromagnetic waves when it is traveling in a vacuum? What is not a possible value of the wavelength of the named electromagnetic waves when it is traveling in a vacuum? So X-rays, gamma rays, the wavelength is 3 times 10 power negative 13. I think that is fine. X-rays, 10 power negative 10, that could be fine. Infrared, 10 power negative 6. Let's look at the spectrum. Richard's mother is visiting Uncle Xavier's garden. Here we have the visible spectrum, which ranges from 7 times 10 power negative 7 for red, and 4 times 10 power negative 7 for violet. This is violet, this is red. So infrared is most likely, its fine is going to be times 10 power negative 6. And microwaves will also still be almost times 10 power negative 5 is still infrared, because infrared will range from 10 power negative 6 to around 10. When I add here 2, I'll get 10 power negative 5. So this is still infrared. Therefore, the question is, which is not a possible value of wavelength? So the answer is going to be D. microwaves should be greater than 10 power negative 5, at least 10 power negative 3, 10 power negative 2, and so on and so forth. So this is not going to be true. Two waves P and Q meet at a point X and superpose. Initially, the two waves meet at X in phase, zero phase difference, so that the resultant wave has an amplitude of 14 centimeters at that point. The phase difference between the two waves is then changed so that they meet at X with a phase difference of 180 degrees. The phase difference between the two waves is then changed so that they meet at X with a phase difference of 180 degrees. So we expect a destructive interference at that point. The resultant wave now has an amplitude of 4 centimeters at X. What is the amplitude of one of the waves at point X? So initially, the two waves met in phase. Initially, the two waves meet at X in phase, so that the resultant wave has an amplitude 14.0 centimeters. The phase difference between the two waves is then changed so that they meet at X with a phase difference of 180 degrees. The resultant wave now has amplitude of 4 centimeters at X. What is the amplitude of one of the waves? Sorry, my battery. Sorry. Okay. So initially the two waves meet at X in phase, so that the resultant wave has an amplitude of that. So let's use the principle of superposition. The resultant wave, let's use X for amplitude of X and Y for amplitude of Y. Or no, let's use P and Q. So the amplitude of P is going to be AP plus AQ should give us 14 when there is, because they arrive in phase, the crest adds up with the crest, the trough adds up with the trough, so the amplitudes add up algebraically like that. Then here, for phase difference being 180 degrees, there is destructive interference. It means if we think of amplitude of P being greater and amplitude of Q being smaller, here algebraically one must be positive and one must be negative, because we now see a smaller amplitude. Therefore, this is going to be amplitude of P plus negative amplitude of Q is going to be equal to 4. So we have two equations to solve. When I add the two equations, equation number 1 plus equation number 2, I will have that twice. AP is going to be the sum of 14 plus 4, which is 18. So it means amplitude of P is most likely going to be 18 divided by 2, which is 9 centimeters. If amplitude of P is 9 centimeters, then we go and solve for the other amplitude. Using maybe the first equation, AP plus AQ is equal to 14. It means AQ is going to be 14 minus 9, which is going to be 5. Or we can use the second equation, AP minus AQ is equal to 4, which still means that AQ is going to be actually 5 centimeters. So the question was, what is the amplitude of one of the waves at point X? So the answer is going to be 5. 18 cannot be correct because it is not one of those. It is not going to be the amplitude of one of the waves. A water wave is diffracted as it passes through a gap between two barriers in a ripple tank. The wave is observed to spread out as it moves through the gap. Which two factors affect the amount of diffraction observed? Remember, diffraction depends on wavelength and the size of the gap. The wavelength should be comparable to the size of the gap. In other words, the wavelength should be almost of the same order as the size of the gap. So let's check. We just look for that answer where the wavelength is almost. Which two factors both affect the amount of diffraction observed? The amplitude and the frequency. Amplitude does not. Frequency, that is wavelength, amplitude and width. Amplitude does not. The wavelength and amplitude. Amplitude does not. The wavelength of the incident wave and the width of the gap. So that is the answer, because I said diffraction is maximum when the wavelength is approximately the same as the size of the gap. So the wavelength and the size of the gap or width of the gap affects diffraction. Two sources of microwaves P and Q produce coherent waves with a phase difference of 180 degrees. The waves have the same wavelength. Phase difference is 180 degrees. The waves have the same wavelength, lambda. At point S, there is a minimum in the interference pattern produced by waves from the two sources. The distance QS minus PS is called the path difference. Which expression could represent the path difference? Because there is a minimum at S, and the phase difference, if there is a minimum, that is destructive interference. So we know that path difference is going to be equal to N plus a half times wavelength. That is path difference if there is destructive interference, and for n should be starting from 0, 1, 2, and so on and so forth. So for n equals to 0, the path difference is going to be n equals to 0, path difference will be lambda over 2, n equals to 1. At the point S, there is a minimum in the interference pattern produced by waves from the two sources. The distance QS and PS is called the path difference. So if there is a minimum, then the path difference is going to be equal to lambda over 2 for the first minimum. For the second minimum, it will be 3 over 2 lambda. But then, of course, the next one will be 5 over 2 lambda. But this is only true if the two sources had initially a phase difference of 0. But because the phase difference between the two sources was initially 180, that is half a cycle ahead, one was half a cycle ahead of the other, and therefore it means the path difference cannot be lambda over 2 or 3 lambda over 2, but we can add 1 cycle on each of these. So if we can add half a cycle on each of these, because 180 degrees corresponds to 1 over 2, that is half a cycle. So when I add a half a cycle on this one, I get lambda. When I add half a cycle on this one plus half a cycle, I get 2 lambda. When I add plus half a cycle here, I get 3 lambda. So I have to look for lambda, 2 lambda, 3 lambda, and so on and so forth. Therefore, the expression could be lambda over 2. I am saying if they initially had a phase difference, if this was initially 0, and then there is a minimum at S, then we can simply say that the path difference is going to be lambda over 2. But because the phase difference of the sources themselves was 180 degrees, where we expect a maximum, we shall find there a minimum. And where we expect a minimum, we shall actually find there a maximum for constructive and destructive interferences. So we expected that if the phase difference between the two sources was initially 0 degrees Celsius, we would expect that at point S, there is a maximum. Unfortunately, since the phase difference is 180 degrees between the two sources, at point S, it is actually becoming a minimum. Therefore, it means the path difference lambda is therefore going to be a half lambda plus half a cycle. How did I circle this? This is lambda, half lambda plus half lambda, which is lambda. Initially, if it was just destructive interference, the path difference would be lambda over 2. That is, if the two sources had a 0 phase difference. But because initially the two sources had phase difference of 180 degrees, that is half a cycle. So I added this half a cycle to this half initial path difference. If the phase difference was to be 0, giving me a total of 1 wavelength. So the answer is going to be C, not B. A beam of red laser light of wavelength 633 nanometers is incident normally on a diffraction grating with 600 lines per millimeter. At this point now you'll notice that number of lines change from per millimeter to per meter, you multiply by 1,000. So this will be 600,000 lines per meter. Okay. The beam of red light is now replaced by a beam of blue light of wavelength 440 nanometers. A replacement diffraction grating is used so that the first order maximum of blue light appears at the same position on the screen as the first order maximum of red light. That means theta has not changed. How many lines per millimeter? Oh, we are the value of number of lines remaining in per millimeter. How many lines per millimeter are there in the replacement diffraction grating? Okay. So we know for diffraction grating, n times lambda is equal to d sine of theta. So n times lambda is equal to, where there is d, we are putting there 1 over the number of lines sine of theta. So n, number of lines, is going to be sine theta divided by n times lambda. So they are saying the beam of red light is now replaced by a beam of blue laser light. So for red, the number of lines, this was equal to 600 lines per millimeter. Then for the second one, the number of lines is going to be equal to, okay, so the beam of red light is now replaced by a beam of blue laser. This was red. Now this is blue. Is replaced by a beam of blue laser light of wavelength 400. So I'm going to change this. So this will be a replacement diffraction grating is used so that the first order maxima of the blue light appears at the same position on the screen as the first order maximum of red light. So this is remaining sine theta, and n is still first order. N is still 1, but the wavelength here is 445. Yet the wavelength there was the wavelength here was 633. So the question is how many lines per millimeter are there in the replacement diffraction grating? So I'm going to divide the two equations. So I'll send n for blue divided by n for red, which is 600, is going to be equal to sine theta divided by 1 times 445 times, I get the reciprocal, n is still 1 for red, 1 times 633 divided by sine of theta. So sine theta cancels. So I'll just get 633 divided by 445, then times 600. That gives us 853. So n is equal to, n for blue is 853, which is approximately 850. So we check, the correct answer here is going to be D. A signal frequency of 25 Hertz, that means the period is going to be 1 over f, which is going to be 1 over 25. That is the period. Is displayed on the screen of a CRO as illustrated here. What is the time-based setting? What is the time-based setting? We know that the period is given by the length representing one cycle times the time-based setting. So that is x. Let's see, one cycle is represented by, I think this is one cycle. Those are 2 centimeters. So the period, which is 1 over 25, is represented by 2 centimeters because there are 2 boxes. So those are 2 centimeters times the time-based setting. Remember, this is in seconds. The frequency, the period is in seconds. The period is in seconds. is equal to 2 centimeters times x. So it means x is going to be 1/25 times 2. Remember, in the denominator this is centimeters, in the numerator it is seconds. So the answer is going to be seconds per centimeter. So this is going to be, but the answers given here are in milli. And to bring a prefix, we divide by its value. So 1 divided by 50, that is 0.02 seconds per centimeter. Then to change it to milli, we divide this by 1 exponent -3, which is going to be 20 milliseconds. So this is 20 milliseconds per centimeter, which makes our answer to be B. Two identical waves are produced by sources at points P and Q. The waves travel along different paths to reach point R as shown in that figure. Both waves have a wavelength of 6 centimeters. The waves are in phase at point R. The waves are in phase at point R. What is the phase difference between the waves as they leave points P and Q? So if they are in phase at point R, let's first find the path difference. Path difference is equal to 100 minus 80, which is going to be 20 centimeters. So we divide the path difference by the wavelength, which will be 20 divided by 6, and 20 divided by 6. 20 divided by 6, that is 3.3 recurring. So this is going to be, okay, the path difference is going to be 20/6. Now we want the phase difference between the waves as they leave points P and Q. So phase difference is going to be equal to 360 degrees. Both waves have a wavelength of 6 centimeters. The waves are in phase at point R. That means the phase difference here is going to be 0, or it is going to be 360 degrees. But then the path difference is 20, and we are seeing that the path difference, okay, so the phase difference is going to be let me see the easier way to do this. Phase difference, so if they arrive in phase here and the path difference is 20, okay, the phase difference will be 360 degrees into x over wavelength. Let's check this. This will be 360. X is the distance out of step, which is going to be 20 centimeters divided by the wavelength, which is 6. So we can check. This is going to be, I think that is going to be 360 times 20 divided by 6. 360 times 20 divided by 6. Sorry. The path difference is 60 divided by wavelength. Okay, so this is going to be 1200 degrees. But then if I was to look at this in this scenario, 20 divided by 6, these are actually 3 and 2/6, I think. 6 times 2 is 6 times 3 is 18 plus 2, that is 20/6. That means there are 3 complete cycles, then plus 2/6. So this is what is out of step. So I'll use this as the distance out of step of these two sources. So the first difference here is going to be 360 into where there is x over wavelength. I'll put there 2/6, which makes this to be that is 60 times 2, and that gives us 120 degrees. So the first difference between the waves as they leave points P and Q, if they arrive here in phase, then the extra part 2/3, which is 1/3, is the phase difference between the two sources if they arrive here in phase. Therefore, the phase difference between the waves as they leave points P and Q is going to be 120 degrees. So I'll just ignore this first part because it is going to confuse many of us. So I am saying if we had 20/6 as the ratio of the path difference to wavelength, this gives us 3 cycles and 2/6, which could be 3 cycles plus 1/3. That means for 3 cycles, if there was nothing else, that would still be in phase. It means the sources would have been also in phase. But then there is this part which is 2/3. So this is going to be the distance out of step, or this corresponds to the distance out of step of the two sources, of the two waves produced from the two sources. That means I would investigate this from phase is equal to 360 times 2/6, which gives us 120 degrees. Okay. A longitudinal wave traveling from left to right has vibrations parallel to the direction. What is wrong with this? Vibrations parallel to the direction of transverse, of transfer of energy by the wave. The wave can be represented on a graph showing the variation with the distance of the displacement of the particles from their equilibrium position at one instant. Note that the wave is traveling from left to right, and this graph is showing distance from the source. Which source is on the left? Which point on the graph is the center of a compression? Of course, at a compression, particles are under maximum pressure, which means the displacement must be 0. But then because the wave is coming from the right, we have 2 points where displacement is 0, but the wave is coming from this side, which means the particle and this point here is nearer the left-hand side where the wave is coming from, so it is under more compression, under more pressure than the other part, which is far away on the right-hand side, since the wave is traveling from the left. Therefore, the question was which point on the graph is the center of a compression? Therefore, the center of a compression is going to be B, because this corresponds to a point where the pressure is extremely maximum. A stationary wave is formed from 2 identical sound waves. A microphone is placed at a position of maximum loudness. It is then moved. It is then moved to. It is then moved to. It is then moved along the stationary wave from this first position of maximum loudness to the fourth position of maximum loudness. The microphone moves a distance of 12 centimeters. The speed of sound is 330 meters per second. What is the frequency of the sound wave? So we know that V is equal to lambda times F. We have V. The microphone moves a distance of 12 from. It is then moved along the stationary wave from the first position of maximum loudness to the fourth position. Let's try to sketch this. Let's try to sketch this here. If we assume that this is the position of first loudness, second loudness, third loudness, fourth loudness, the microphone is moved through the position of first loudness to the fourth position of maximum loudness. First position of maximum to first to fourth position of maximum. So that means the distance it has moved through is going to be a quarter plus a quarter, that is a half. A quarter plus a quarter, another half, that is one wavelength. A quarter plus a quarter, so this is 1, 2, 3, 4, 5, 6 quarters. So that is 6 quarters, that is 6 over 4. 6 over 4, that is going to be 1.5. 1.5 a cycle. So this is 1.5 a cycle. So it means the distance of 12 centimeters is equal to 6 over 4 wavelength. So that means our wavelength is going to be 4 times 12 divided by 6 in centimeters, which is going to be, that is 8 centimeters. So the wavelength is 8 centimeters. So let's find the frequency. So the frequency therefore is going to be V divided by wavelength, which is 8 times 10 power negative 2. And V, remember, is 330. 330 divided by 8 exponent negative 2. So we are getting an answer of 4125, which is approximately 4100. So our answer is going to be A. An ambulance has a siren that emits sound of a constant frequency. The ambulance is moving directed towards a stationary observer. The ambulance decelerates as it is approaching the observer and then accelerates after it has passed the observer. So if it decelerates, it means speed is decreasing. How does the frequency of the sound heard by the observer change as the ambulance is approaching and as it is moving away from the observer? So frequency, if it is approaching, Vf naught is going to be V over V. If it is approaching, this is going to be minus V of the source, and then this is going to be times Fs. Frequency, speed of the source is, if it is decelerating, speed of the source is decreasing. The speed of the source is decreasing, which means the denominator is going to be increasing. Therefore, F naught is going to be increasing. So the first part approaching, it must be approaching, no, because speed of the source is decreasing, this difference is going to be bigger. It will be increasing. That means F naught must be decreasing. So we have A and B. We eliminate C and D. Then away, F naught is going to be V divided by V plus speed of the source times Fs. Because it accelerates, it means speed of the source is increasing, making the denominator to become bigger. And if the denominator becomes bigger, it means this is going to become smaller. Therefore, F naught also decreases. So approaching the observer, frequency decreases. Moving away from the observer, it also decreases. We have seen how it decreases in both cases. In the first case, it is decelerating. So the speed Vs is becoming smaller, which means this difference here is going to become bigger as Vs becomes smaller, which means the observed frequency decreases. The second case, it is plus because it is moving away, but it is accelerating, meaning Vs is increasing. The sum is also going to be bigger, which reduces this fraction, so F naught becomes smaller. So decreases, decreases. Microwaves in a vacuum travel at a speed x and have a wavelength of order of y, of magnitude y. What are the speed and a possible order of magnitude of wavelength of X-rays? Of course, the speed must be the same. The speed is the same, so we eliminate C and D. They travel at the speed of light 3 times 10 power 8, X-rays and microwaves. So we remain with two options. We want what are the speed and a possible order of magnitude of wavelength of X-rays in a vacuum. We have seen for microwaves the magnitude is of order y. How about for X-rays? So Richard's mother is visiting Uncle Xavier's garden. So X-rays have a smaller wavelength than microwaves. X-rays have a smaller wavelength than microwaves. Now when you say for X-rays it is going to be 10 power negative 4 times the order of y, there's a possibility that this value here, X-rays must have a smaller, X-rays must have a smaller what? Wavelength than microwaves. So when we say that uh, microwaves have a wavelength of order of magnitude y, then when you look at this part here, this is 7 times 10 power negative 7 for radio waves, for red, and 4 times 10 power negative 7 for violet. Then X-rays are on the other side. So the order must be increasing, so this should be a more negative power rather than 10 power negative 4. So this means the answer is going to be 10 power negative 8 times the order of y. The diagram shows part of a stationary wave on a string. X and y are points on the string. The vibrations at X and Y are 180 degrees out of phase. Yes, this is a segment, the other one is a segment. The vibrations must be 180 degrees out of phase. What is the distance between X and Y? What is the distance between X and Y? So this is an antinode. This is also going to be an antinode. The distance between two successive antinodes is always half wavelength. So the answer is just B. Which wave behavior is shown here? I think this is diffraction. Everyone can see that this is diffraction, spreading of waves into regions of geometrical shadow. So this is simply going to be diffraction, nothing else. A teacher sets up the apparatus shown to demonstrate a double slit interference pattern on the screen. Which change to the apparatus will increase the fringe spacing? Remember, fringe spacing is x. So since it is a double slit, lambda is equal to ax divided by d. D is represented as r, and the distance a is represented as q. So lambda is equal to q times the fringe spacing. Where there is d, I'm putting there r. So which change to the apparatus will increase the fringe spacing? Either we increase the wavelength or we increase r. When we increase q, x decreases. So decrease p, that one has no effect. Decrease p, that one will not have any effect. Decrease the distance q. Because x is inversely proportional to q, if q decreases, x increases. So the answer is most likely going to be B. Decrease the distance r. X is directly proportional to r. If r decreases, x decreases. Decrease the wavelength of the light. X is directly proportional to the wavelength. When wavelength decreases, x also decreases. So the answer is B. Two lasers emit light in a vacuum. One laser emits red light and the other emits green light. Which property of the light from the two lasers must be different? So they have the same speed, of course. That one is not different. Because they have the same speed, two lasers emit light in a vacuum. One laser emits red and the other emits green. So these ones have different wavelengths and therefore they have different frequencies. Therefore, the answer here is going to be frequency. Which property must be different? That is frequency. Because red has approximately 7 times 10 power negative 7 wavelength. And remember, frequency is inversely proportional to wavelength. Red has a longer wavelength than green, so red has a smaller frequency than green. Light of a single unknown wavelength and blue light of a single wavelength are both incident normally on a diffraction grating. two diffraction patterns are produced, one of each wavelength of light. The third order maximum for the blue light occurs at the same angle as the second order maximum for the light of unknown wavelength. The wavelength of the blue light is that one. What is the unknown wavelength? So since this is a diffraction grating, the diffraction grating formula, lambda is equal to AX divided by D. So we have blue. They have given us the wavelength of blue. I'm going to come up with two equations. For blue, lambda is 480 is equal to A is going to remain the same. X, they said, no, this is not a diffraction grating. This one is a double slit formula. For diffraction grating, n lambda is equal to d sine theta. Okay, so the third order maximum for blue light. So for blue, n is 3. Then the wavelength has been given as 480 is equal to d is the same because they are passing through the same grating. Then times sine of theta. The third order maximum for blue light occurs at the same angle, so sine theta is going to remain the same angle as the second order. So for the unknown light, n small n is 2. Its wavelength is not known, d is the same, and then sine theta is the same. So we want lambda. I'm just going to combine these two equations. That means lambda is going to be equal to 3 times 480 divided by 2 when I make lambda the subject. 3 times 480 divided by 2, and this is giving me 720. So the answer is 720 nanometers. Two particles in a progressive wave are a distance 10 centimeters apart. The two graphs show the variation with the time of the displacement d of the two particles. What could be represented by the two graphs? What could be represented by the two graphs? Particles in a longitudinal wave with a compression and the nearest rarefaction separated by 10 centimeters. Two particles in a progressive wave are a distance 10 centimeters apart. Two particles in a progressive wave are a distance 10 centimeters apart. The two graphs show the variation with the time t of the displacement d of the two particles. So this is for the first particle at t equals to 0. The other particle is at maximum displacement upwards, and the other particle is also at maximum displacement downwards. Okay, what could be represented by the two graphs? Particles in a longitudinal wave with a compression and the nearest rarefaction separated by 10 centimeters. Particles in a longitudinal wave. Particles in a longitudinal wave with a compression and the nearest rarefaction separated by 20 centimeters. Particles in a longitudinal wave with a compression and the nearest rarefaction. Compression, that is, so this is going to be the distance between a compression and the nearest rarefaction being twice the distance between the two particles. This is not true. Particles in a transverse wave with a peak and the nearest trough separated by 20 centimeters. In other words, the distance between a peak and the nearest trough is twice the distance between the two particles. Yet at t equals to 0, this particle is at maximum displacement upwards. The other at t equals 0, this particle is at maximum displacement at the bottom. This is not going to be possible. This will not be true. Particles in a transverse wave with two adjacent peaks separated by 10 centimeters. Two adjacent peaks separated by 10 centimeters. Two adjacent peaks separated by 10 centimeters. These cannot be adjacent peaks because at equals to 0, the other particle, the displacement, let's check. I think the displacement here is almost the same as this one. Okay. Particles in a transverse wave with two adjacent peaks separated by 10 centimeters. Adjacent peaks, particles vibrate. In a transverse wave, adjacent peaks particles must be vibrating in the same direction. Yet here it is showing they are not vibrating in the same direction. So this one is also not true. So it means the answer is going to be A. Particles in a longitudinal wave with a compression and the nearest rarefaction separated by 10 centimeters, because the compression particles particles vibrate in the opposite direction to those in a rarefaction. They are actually vibrating in opposite direction. They must be have reached at maximum displacement in opposite direction. So the answer is going to be A. A sound wave is detected by a microphone and is connected to a cathode ray oscilloscope. The screen of the CRO displays a waveform as shown here. The time base is set to 20 microseconds per division. What is the frequency of the sound wave? So we want frequency. We know frequency is going to be 1 over the period. The period is going to be 1 over the length, representing this one cycle, times x, which I'm calling the time base setting. Okay, so this is going to be 1 divided by the length representing 1 cycle. Let's look for 1 cycle if it is possible. So I have to look for a point. Okay, this point is fine and this point is fine. So how many cycles are there? So this is 1.5. So 1.5 cycles are corresponding to 5 divisions. 1, 2, 3, 4, 5 divisions. So 1.5 cycles in 5 divisions. This is equal to 5 divisions. So it means 1 cycle, remember 1.5 is 3 over 2, equals to 5 divisions. So it means 1 cycle is going to be 2 times 5 divided by 3 divisions. 1 cycle takes 2 times 5 over 3 divisions, which is 10 over 3 divisions. So let's find now the frequency is going to be 10 over 3. 10 over 3, that is the length representing 1 cycle, times the time base setting, which is 20. A micro is times 10 power negative 6. So the 3 has gone up. So I'll say 3 divided by 10 times 20 exponent negative 6. So that is going to be 15,000. So the frequency is 15,000. So the answer here is going to be B. A person stands at the side of a straight railway track. A train moves towards the person and emits sound from its whistle. The person hears a sound of frequency 1690 Hz. As the train approaches him, the person then hears sound of frequency 1500 as the train moves away from him. The speed of sound in air is 340. What is the speed of the train? So here it is moving towards him. So the frequency F0, which is 1690, is going to be the speed of sound in air, which is 340, divided by 340. Because it is moving towards, we shall subtract minus the speed of the train. This is times the frequency of the source. When it is moving away, the observed frequency F0, which we have seen as 1500, is going to be 340 divided by 340. Because it is moving away, we shall add here plus the speed of the source, because here the frequency is low. So this is times Fs. So we just combine these two equations by division. When I divide the two equations, I will have 1690 divided by 1500 equals 2. When I divide the Fs cancels, I remain with the 340 divided by 340 minus Vs times, I get the reciprocal of the one in the down here, which is going to be 340 plus Vs over 340. I wanted you to see that 340 cancels out. So I'm just going to solve this equation. This will be 1690 into 340 minus Vs equals to 1500 into 340 plus Vs. So we just open the bracket or collect like terms. Okay, so opening the bracket, I'll have 1690 times 340. So that is 574,600 minus 1690 Vs equals to 1500 times 340, which is 510,000. Then plus 1500 Vs. I'm doing all this for PCB students, but this would be very easy. So I'm collecting like terms. So I'll say 574,600 minus the answer. So that is 64600 on one side equals 2. I take this one the other side. The other side I have 1500 plus 1690, which is going to be 3190 times Vs. Now I divide 64600 divided by 3190. So this is giving me 20. So Vs is equal to 20 meters per second. So the answer is going to be A. Which list shows electromagnetic waves in order of decreasing frequency? Richard's mother is visiting Uncle Xavier's garden. So this is increasing frequency. This is decreasing frequency. Frequency decreases this side. So here frequency is decreasing. Okay. So radio waves cannot come because we want in order of decreasing frequency. So we start with the highest frequency. The highest is gamma. So we eliminate C and D because we want decreasing frequency. Then the next is X. X-ray is not there. Ultraviolet. So we have infrared in A. That means the answer remains B because ultraviolet must be the second. A pipe of length L is open at one end and closed at the other end. A loudspeaker is at the open end and emits a sound wave into the pipe. When a stationary wave is formed, there is an antinode at the open end of the pipe. Which wavelength of sound could be used to produce a stationary wave? So if there is an antinode there, we expect a node the other side. So the length is going to represent a quarter of a wavelength because there's just a quarter cycle there for the fundamental mode. So it means lambda is going to be 4L. So the question is, which wavelength of sound could be used to produce a stationary wave? So since here we only have odd harmonics, the fundamental should be 4L. 4L is not there. The fundamental is a quarter wavelength. Then the next one is going to be, we can try the next one. We don't have 4L here, so I will try the next one. So I'm going to use green for the next one. So we shall introduce an antinode, there. So for that one, L is going to represent, I will have a half plus a quarter, that is a half plus a quarter wavelength, which is going to be 4, that is 3 over 4 wavelength, which means wavelength is going to be 4L divided by 3, and that one we have it, so the answer is C. Which diagram best shows how water waves diffract when they pass through a gap in a barrier? Remember, the wavelength does not change. The wavelength does not change. So look at the estimated wavelength. And diffraction is maximum when the wavelength is approximately the same as the size of the gap. Okay. So we can see here, here the wavelength is almost the same, but you notice that the size of the gap is very small. So we cannot have, this one is showing that the wavelength has increased, so that one will automatically eliminate it. This one is showing that there is completely no bending, that one we just ignore it. So we remain with these two. So here you notice that the wavelength of the wave is almost the same as the size of the gap. So diffraction is maximum and the wavelength has not changed. So it means this is the most appropriate answer. That is going to be the most appropriate, because bending cannot start from almost from the regions of geometric shadow. So it should start from around here and then it goes on spreading. So the answer is going to be B. So A is also wrong. In a two-source interference experiment, light of a single frequency is incident on a double slit. The light waves emerging from the slits are coherent. What is meant by coherent? Of course, coherent, they must be maintaining a constant phase difference. So let's see the available answers here. The light waves emerging from the slits are coherent. What is meant by coherent? The waves are in phase. The waves have a constant phase difference, so the answer is B. A parallel beam of light consists of light of wavelength 420 nanometers and light of wavelength 630 nanometers. The light is incident normal on a diffraction grating. The diffraction maxima for the two wavelengths overlap only at an angle of 31 degrees from the direction of incident light beam. What could be the line spacing of the diffraction grating? So we know that for a diffraction grating, n lambda is equal to d sine theta. Because they overlap at 31 degrees, the diffraction maxima for the two wavelengths overlap only at an angle of 31 degrees from the direction of the incident light beam. What could be the line spacing? That is what is D. So let's say let's first find the value of n here. So we shall have that n, the diffraction maxima for the two wavelengths, overlap only at an angle of 31 degrees from the direction of the incident light beam. So let's say this is n1 for the first light. So n1 times the wavelength, which is 420, I will not change the units, is going to be d sine of 31. Then the second one, I'll call this n2 times the wavelength, which is 630 is going to be equal to d sine of 31. They only overlap at that point. That means that this part may cancel out, and I will say that, or if I equate the two parts, so I have that N1 times 420 is equal to N2 times 630. So N1 over N2 is going to be equal to 630 divided by 420. N1 over N2 is equal to that. In other words, N1 is going to be equal to 63 over 42 N2. Let me see if this is divisible first of all. 63 divided by 42, that is 3 over 2. So it means N1 is 3 over 2 times N2. N1 is 3 over 2 times N2. Okay, now we can find D. We can check for N1 equals to 1. For N1 equals to 1, for N1 equals to 1, it means N2 is equal to 2 over 3, and that is not an integer. That will not be possible. Let's check N1 equals to 2. N1 equals to 2. N2 is going to be equal to 4 over 3. That will also not be possible because it will not be an integer. N1 equals to 4. Now let's check N1 equals to 3. If N1 is equal to 3, N2 is going to be equal to 2. So if N1 equals 3, N2 is going to be equal to 2. So I can now use N of those to find D. So N must be, if N1 is 3, N2 must be 2. If N1 is 3, N2 must be 2. So like I can now substitute. So I'm going to use 3 times the wavelength, which is 420, times 10 power negative 9 is going to be equal to D times sine of 31. Okay, so I have 3 times 420 exponent negative 9, which is equal to that, divided by sine of 31, which is equal to 2.5. No, I did sine of 30 instead of 31. Let me repeat. 3 times 420 exponent negative 9 divided by sine of 31. That is 2.4 times 10 power negative 6. So D is equal to 2.4 times 10 power negative 6, which is equal to 2.4 micrometers. So the answer is going to be C. Okay, so the analysis there is very interesting. We didn't know the orders for which they overlap. That's why I did two equations here. But D is the same, sine 31 is the same, so I equated the two equations here. So I realized that N1 is going to be 3 over 2 N2, but N1, these values of N must be integers, must be whole numbers. So that's why I couldn't take the combination of N equals to 1 could not work, equals to 2, N1 equals 2 could not work. So I started with N equals to 3, N1 equals 3, which means N2 was 2. So if I use N2 as 2, I should get the same value of D. A transverse progressive wave of wavelength lambda is set up on a stretched string. The graph shows the variation of displacement y with distance x at a particular instant of time. The wave has displacement positive y1 at distance x equals to lambda over 8. Okay. What are the next two values of x where the displacement is again equal to positive y1? Those were easy. The first one is here, just on the same horizontal level, it is here. Then the next one, because it must be positive, the next one should be here. So this should be plus lambda over 8. This one should be minus. I'm going to subtract lambda over 8 from lambda. So the first one is lambda over 2 minus lambda over 8, which is equal to LCM is 8. So that is 4 lambda minus lambda, which is 3 lambda over 8. So the first one is 3 lambda over 8. It means I've ignored this one and this one. The second one is here, which is 1 full cycle plus lambda over 8, which is equal to, I think, 9 over 8 times lambda. So the answer is going to be B. The graph shows the variation with time t of the displacement of an air particle as a progressive sound wave passes through the air. The speed of the sound is 330. What is the wavelength of the wave? Wavelength of the wave. So V is equal to lambda times F, which implies we have lambda, F is 1 over t, so this is lambda over t. This is going to be equal to lambda over t, where t is going to be the period. So it means lambda is going to be V times t. Let's substitute. V is 330, then times the period. So this is 5, that is 25. 25 minus 5, I think that is 20. So this is 20 times 10 power negative 3 because it is in milliseconds. 330 times 20 exponent negative 3, which gives us 6.6. So our answer is going to be A. The microphone is connected to a cathode ray oscilloscope. A sound of constant frequency is detected by the microphone. The screen of the CRO is shown. Time base is set at 1.0 milliseconds per centimeter. What is the frequency? So here we have 1, 2, 3, 4. 4 divisions of 4 centimeters are representing one cycle. So frequency is equal to 1 over period, which is 1 over the length of one cycle times the time base setting, which is 1 over the length of one cycle is 4 centimeters times the time base setting, which is 1.0 times 10 power negative 3. So we have 1 divided by 4 exponent negative 3, which gives us 250. So the answer is A. A train's whistle is emitting sound of frequency 500 Hz as the train moves with their speed along the straight track. The train moves directed towards the stationary observer standing next to the track and then passes the observer. The speed of sound in air is 330. What is the difference between the frequency of the sound heard by the observer before and after the train has passed the observer? So towards observed frequency is going to be the speed of sound 330 divided by 330. Because it is towards, the frequency is higher, so I would say minus 20. Then this is times 500. Then away, when it's moving away, the observed frequency is going to be 330 divided by 330 plus 20, then times 500. So we can compute those. So 330 times 500 divided by 310. So that is 532.3. 532.3 hertz. Then the second one, 330 times 500 divided by 300, and that is 350, which is 471.4. 471.4. Now we want the difference. So just subtract 532 minus 471. That is 61. So the answer here is going to be D. Gamma rays, microwaves, visible light are four regions of electromagnetic spectrum. Which list shows the four regions in order of increasing wavelength? Radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma. This one has the highest wavelength. So if there is radio waves, it should come at the end. Next is microwaves. If there are microwaves, it should come at the end. If it is not there, so we are looking at increasing wavelength. So this is not true, that is decreasing. This is also not true. If there are microwaves, it should come at the end, and this is also not true, which means our answer should be B, because wavelength increases as we move towards radio waves. Since there are no radio waves, microwaves should come at the end. To produce a stationary wave, two waves must travel in opposite directions in the same space. Which statement about the properties of the two waves must also be correct? To produce a stationary wave, of course, they must have the same frequencies and the same wavelength. They must travel with the same speed, that is in opposite directions. So waves must have equal frequencies but different speeds. That's not true. Waves must have equal speeds, very true, but different wavelengths. That's not true. Waves must have equal speeds, frequencies, and wavelengths. So the answer is C. The speed of sound in air is 330. Which size of architectural features in a large concert hall would best diffract sound waves of frequency 0.44 kilohertz? Okay, so let's find the wavelength here first. Let's first find the wavelength. So wavelength is going to be equal to V over the frequency, that is 330, divided by the frequency, which is 0.44 times 10 power 3. 330 divided by 0.44 exponent 3. So that is 0.75 meters. So wavelength is 0.75 in meters. So the wavelength, remember, should have the same order as, almost the same order um, the diffraction, the gap. So we can try to convert this to centimeters. There is no centimeters here, to millimeters. So times 1,000. So that one times 1,000 is 750. So the answer here is going to be B, 750 millimeters. The wavelength should be of the same order as the architectural feature. Yeah, English is not my first language. Double slit interference pattern using red light of wavelength 7 times 10 power negative 7 has a fringe spacing. So this is going to be this is wavelength, this is fringe spacing, that is X. Which fringe spacing would be observed for the same arrangement of apparatus but using blue of this wavelength? So for a double slit, lambda is equal to AX divided by D. So it means A and D are remaining the same. So for the first one, the wavelength is 7 times 10 power negative 7 is equal to a constant, because A over D are going to be constants, then times 3.5 millimeters. For the second one, the wavelength is 4.5 times 10 power negative 7 is equal to the same constant, then times X. We just divide. So I make X the subject, K cancels out. So X is going to be equal to, okay, I'm dividing this equation by the other one. So X is going to be equal to 4.5 times 10 power negative 7 divided by 7 times 10 power negative 7 times 3.5. We just divide the two equations. Then make X the subject. So I'm remaining with 4.5 divided by 7 the power of 7 of 10 has cancelled, times 3.5. And 9 divided by 4, I think it is 2.25, which is 2.3. So the answer is going to be A. 2.25 millimeters, which is, I didn't change the units of x, that's why you see I'm finding millimeters. A beam of light of a single wavelength is incident normal on a diffraction grating. The angle of diffraction theta is measured for each order of diffraction, and the distance between adjacent slits is in the diffraction grating is d. A graph is plotted to determine the wavelength of the light. Which graph should be plotted and how is the wavelength determined from the graph? So we have the angle of diffraction is measured for each order n. So we know that n lambda is equal to d sine theta. So n is the independent variable. N is the independent variable. N is the independent variable. So we cannot plot a graph of d over n. We cannot easily plot a graph of d over n, so it means I will ignore these two. Now n is the independent variable. When we change n for the same wavelength, when we change n, of course, d is remaining the same. When we change n, the angle also increases. So sine theta is going to be the dependent variable. So the dependent variable is most likely going to be, the dependent is most likely going to be put on, it is always better to put the dependent on the x-axis, I mean on the y-axis, and the independent on the x-axis. But in this case, we have n on the y-axis, and we have sine theta, d sine theta on the x-axis. But now let's concentrate on the gradient. If I put n on the y-axis, y is equal to mx plus c. There is no c here. If I put n on the y-axis and d sine theta on the x-axis, the gradient must be 1 over lambda. The gradient m is going to be 1 over lambda, which means lambda is equal to 1 over the gradient. So it means the answer is going to be B. A transmitter emits a pulse of electromagnetic waves towards a reflector. The pulse is reflected and returns to the transmitter. A detector is located at the transmitter. The emitted pulse and the reflected pulse are displayed on a CRO. Because the detector is at the transmitter, it means the distance shown here is towards the reflector and back. So the distance here is between transmitting and receiving. The pulse takes 6.3 microseconds to travel from the transmitter to the reflector. What is the time-based setting of the CRO? So the distance between the reflected and transmitted is going to be, we can estimate this. We can estimate this, or we can even just look at the centers of this. So the distance between the pulses is 1, 2, 3. So those are 3 centimeters. So the distance is 3 centimeters. So let's see the time between the pulses. Time between incident and reflected is going to be 3 centimeters times the time-based setting, which I'm calling x. But I said the pulse takes 6.3 microseconds to travel from the transmitter, the receiver, to the reflector. What is the time-based setting of this CRO? So this time I'm going to divide it, because the time here is between transmission and reflection, sending and actually receiving. And this time, the time between the pulses is equal to 3 centimeters times the time-based setting. So the pulse takes 6.3 microseconds to travel from the transmitter to the reflector. So I'm going to divide this by 2 to equate to 6.3. So 6.3 is going to be 3 centimeters divided by 2 times the time-based setting x. So we want the time-based setting, so that will be 6.3 times 2, then divide by 3, which is 4.2. So the time-based setting x is going to be 4.2 microseconds per centimeter. So the answer is C. This might be confusing. The time here between this point and this point is the time towards the reflector and coming back, because they say the microphone and the source of the sound, the transmitter and the microphone are at the same point. And what is seen here is the time between transmitting and receiving. So that time is twice. That's why I divided here by 2. The time t that is between the pulses, 3 centimeters times the time-based setting. But I'm saying this time is twice. Yet the time which was given here is just one way. From the transmitter to the reflector is 6.3. That's why I divided this by 2. This gives us the time-based setting as 4.2. Because this was in microseconds, so it is 4.2 microseconds per centimeter. A wave of frequency 15 Hz travels at 24 meters per second through a medium. What is the phase difference between 2 points 2 meters apart? So that is easy. Phase difference is 360 into the distance apart over wavelength. That will be in degrees. So this is going to be 360. X is 2.0 meters. Then we need the wavelength. So the wavelength is going to be equal to V, which is 24, divided by frequency, which is 15. 24 divided by 15, that is 1.6. So this is 1.6. So because they didn't give an angle, they were given in terms of a cycle, we shall only consider the fraction here. So we have 2 divided by the answer, which is going to be 1.25 times a cycle. Okay, so that is 5. So this is 360 times 5 over 4, which is the same as actually a quarter of a cycle, because 5 over 4 means one cycle. I mean 4 complete cycles and a quarter cycle. So a quarter cycle is the part which is contributing the phase difference. The others are always in phase, because after a complete cycle, it is in phase. So 5 over 4. 5 over 4, that is one cycle and a quarter. Is it one cycle and a quarter? Yes. One cycle and a quarter. This part here is the one which is acting as it is the one which is affecting the phase difference. So the answer is going to be they are out of phase by a quarter a cycle. There is no phase difference. They are out of phase by half a cycle. No, the quarter cycle is very important. They are out of phase by 0.8 of a cycle, which is 1.25, which is the same as the one is one complete cycle, then the other part is a quarter cycle. Which rule describes a longitudinal wave and a medium through which it can travel? A longitudinal wave must travel through a medium. It can't travel through a vacuum. So we ignore this one and this one. So we remain with A and A and B, A and C. But for longitudinal, the particles vibrate parallel to the direction of propagation of the wave. So the answer is A. A sound wave is displayed on the screen of a cathode ray oscilloscope as shown here. The time base is 0.5 milliseconds per division. What is the frequency? So let's say how many divisions represent one cycle? 1, 2, 3. One cycle stops here. So frequency is equal to 1 over period, which is 1 over the length representing one cycle and the time base setting. So that is 1 over. That is going to be 3 divisions representing one cycle times 0.5, but is in milliseconds, so that will be times 10 power negative 3. So 1 divided by 3 times 0.5 exponent -3, which is 666.6 recurring, which is 670. So the answer here is going to be B. An observer is situated at the top of a tall tower. An aeroplane emitting sound at a frequency of 1000 Hz approaches the observer at a speed of 165 meters per second. The speed of sound is 330 meters per second. What is the frequency of the sound received by the observer? So an observer is situated at the top of a tall tower. An aeroplane emitting sound at that frequency approaches the observer. So that is Doppler effect. Observed frequency is going to be the speed of sound, which is 330 over 330. Because it is approaching, this will be minus because the frequency must be higher. The speed of the approaches the observer at a speed of 165. So that's times over minus 165, then times the speed frequency of the source, which is 1000. So it means these two are automatically wrong because they are below. This one is also wrong. Even if I don't capture, this is also wrong. It means it is the exact frequency. It is supposed to be higher. So the answer is D. What is the order of magnitude of the wavelengths of microwaves and X-rays? The wavelength of microwaves must be greater than that of X-rays. So we check. We begin by that. So we are seeing X-rays here is having a greater wavelength. That is not true. So we remain with C and D. Yes, we are seeing this wavelength of X-rays is less, but what is the order? Let's check. Richard's mother is visiting Uncle Xavier's garden. This one has the highest wavelength. And for the visible light, we have red and violet. This is 7 times 10 power negative 7. Violet is 4 times 10 power negative 7 in meters. So X-ray is this side. That means the power of 10 should be more negative. And it is still more negative. But then infrared, the power of 10 is most likely going to be negative 6. Negative 6 is mostly infrared. This is negative 6 is infrared. That means it should be microwave should be D. So the answer is D. A musical instrument is made using a long tube with a mouthpiece at one end. The other end is open and flared as shown. So it means a musician maintains stationary sound waves with a note at the mouthpiece and an antinode at the other end. So there is a note at the mouthpiece and an antinode at the other end. So it is behaving as if it is a closed pipe. So it means for the fundamental mode, the length L is going to represent a quarter a wavelength, which means the wavelength is going to be 4L. The lowest frequency of sound that the instrument can produce is 92 Hz. Which different frequencies of sound can be produced by the instrument? If we maintain a node at the mouthpiece and an antinode at the other end, this means we're only going to have odd harmonics. Fn is going to be n times f naught, where n is going to be an odd number. It is behaving like a closed pipe. So for n equals to 1, f is equal to f naught, f1 is equal to f naught. So the first frequency is that one. The second odd number we have 1, 2, we have 1, 3. This one is missing. 4 is missing. We have 5. 6 is missing. We have 7. So the second one is going to be 3 times 92 because the fundamental is 92. That is 276. That means which different frequencies of sound can be produced by the instrument? 276, it is missing here. The next is 276. This one is not going to be there. So we remain with the C and D. Then the next one is going to be 5 times 92, which is 460. So the answer is going to be C. I've just used the Fn is equal to n times F naught, where n should be an odd number if it is behaving like a closed pipe. N should be an odd number. A water wave passes through a gap between two barriers. The wavefront spread out has shown. What is the name of this phenomenon? That is automatically diffraction. The table shows four possible combinations of values for the laser wavelength, slit separation, and slit screen distance in a two-slit interference experiment to show the interference of visible light on a white screen. Which combination will result in visible fringes being observed? So we check the wavelength. The wavelength of laser wavelength 200 nanometers. This is 2 times 10 power negative 7. That is outside the visible range. 2 times 10 power negative 7. That's outside the visible range. So we ignore A and B. Now this one is in the visible range. The wavelength of 600 is in the visible range. Now let's check the slit separation and slit to screen distance. Which combination will result in visible fringes being observed? So let's check these ones here. Let's find x. So lambda is equal to ax divided by d. So x is going to be lambda times d divided by a. Let's check the first one. 600 times 10 power negative 9 times d, which is 5, divided by a, which is the slit separation, 0.1 times 10 power negative 3. 600 exponent negative 9 times 5, 600 exponent negative 9 times 5 divided by 0.1 exponent negative 3. So that is 0.03 meters times 100, that is 3 centimeters. Let's check the last one also. X is going to be 600 times 10 power negative 9 times 1.0 divided by 100 times 10 power negative 3. Let's check if they are also visible. 600 exponent negative 9, of course, times 1 divided by 100 exponent negative 3. So this is very small, 6 times 10 power negative 6 meters. This is extremely small. They may not be visible, so this will be visible. So the answer is going to be C. So this one is extremely small, may not be visible. Light of wavelength lambda is incidental normally on a diffraction grating as shown here. So we divide this by 2, so it will be phi divided by 2, because theta is always measured from the central maximum. The angle between the two second order maxima is phi. Which expression gives the spacing of the lines on the diffraction grating? So n lambda is equal to the spacing sine of theta. So n is 2. Then wavelength is lambda. Then d sine theta is going to be phi divided by 2. So it means d is going to be twice lambda divided by sine of phi over 2. So our answer here is strictly going to be D. A wave has frequency 5 gigahertz. What is the period of the wave? Period. So frequency is equal to 1 over period, which is 1 over 5 times 10 power giga is 9. So 1 divided by 5 exponent 9. So the period is 2 times 10 power negative 10 in seconds. So that is the period. Yes, period is equal to 1 over frequency. Then we'll have to bring to check what will this one be in picoseconds. Picoseconds divided by 1 exponent negative 12 pico, that is 200 picoseconds. So the answer is A. A sound wave passes through air. The diagram shows the positions of the molecules of the air at one instant. Which distance is equal to the wavelength of the wave? Of course, wavelength is going to be equal to the distance between two successive compressions or two successive rarefactions. So it can be P to Q to R or Q to S. P to R is not there, Q to S is there, so the answer is D. This is going to be a wavelength, distance between two successive compressions, or this one here, distance between two successive rarefactions. These are rarefactions, and these are compressions. The top row of bars represents a set of particles inside the Earth and at rest. The lower row represents the same point particles at one instant as a longitudinal wave passes from left to right through the Earth. What should be measured to determine the amplitude of the oscillations of the particles in the lower row as the wave passes? So what should be measured to determine the amplitude? So half the maximum displacement of the particles from their position at rest. That is not amplitude. Amplitude is maximum displacement from equilibrium position. Half the maximum distance apart of the particles. The maximum displacement of the particles from their rest position. That will give us the amplitude. A straight tube is closed at one end and has a loudspeaker positioned at the open end. The frequency of the loudspeaker is initially very low and is increased slowly. A series of loudness maxima are heard. The stationary wave, which gives the first maximum, has a node at the closed end and an antinode at the open end. That one is very easy. So there's an antinode at the closed end and there's a node at the open end for the fundamental. The stationary wave, which gives the first maxima, has a node at the closed end and an antinode at the open end. The frequency of the loudspeaker is F1 when the first maximum is heard. So it means F1 is going to be V over a lambda. Remember here, lambda is going to be 4L, I mean a quarter L, 4L actually, because this length, L is going to be a quarter of wavelength. So this is going to be V over 4L. What is the frequency of the loudspeaker when the fourth maximum is heard? Fourth maximum. I will sketch this for simplicity. Let me sketch it here. For the same fourth maximum. So this is going to be, I'm going to introduce to increase the frequency so that I have more maximum. So since I want the fourth maximum, the second maximum, this will give us one node. That is the second maximum. The third maxima will give us another node. So we have this one. That is the third maxima. Then the fourth maxima, I will show it here. Excuse me. So the fourth maxima here, I have 1, 2, 3 nodes, so I must introduce a fourth node. So this is 1, 2, no. One, two, three, no. These are too many. I must introduce a fourth node. Now I have 4 nodes, so that is the fourth maximum. So I'm interested in this one here. So the length L is going to be 1 cycle, a half plus a quarter. So that is wavelength plus a half wavelength plus a quarter of wavelength, which means the frequency there is going to be equal to, I'll call it F2, is going to be V over wavelength, which wavelength is going to stand for a half, 1 plus a half plus a quarter, which is 0.25. That is 7 over 4. So here L is equal to 7 over 4 wavelength. So F2 is going to be equal, wavelength is 4 over 7. So F2 is going to be equal to V divided by wavelength, which is 4 over 7 lambda. No, 4L over 7, not lambda. Lambda has disappeared. I've substituted for lambda. So F2 is V over 4L over 7 because I made lambda here the subject. And lambda here is 4L over 7. So it means F2 is going to be the 7 goes up. So it becomes 7 over 4L times V. But we know that V over 4L was actually F1. No, yes, V over 4L was F1. So it means here the answer will be D. So this becomes 7 times F1, which makes the answer to be D. A buzzer emitting sound of frequency 846 Hz is attached to a string and rotated in a horizontal circle. The linear speed of the buzzer is 25 meters per second. The speed of sound is 340. What is the maximum frequency heard by the observer? So the maximum frequency is heard, of course, the maximum frequency is going to be heard when it is moving towards the observer, and the minimum is when it is moving away. At this point and this point is going to be the normal frequency. So F naught is going to be the speed of sound, which is 340 divided by 340, because maximum is heard when it is moving towards. So this would be minus 25. Then we multiply this by the frequency of the source, which is 846. So the maximum heard by the observer should be above 846. So even if I don't check this, it is below. So I remain with these two. So it is going to be 340 divided by open bracket 340 minus 25, then times 846, which is 913. So the answer is going to be D. The diagram shows the principal regions of the electromagnetic spectrum with some details labeled. The diagram is not to scale. What is the typical order of the magnitude of the wavelength of the radiation region Q? So this is increasing wavelength. That means this is the highest. Remenera's mother is visiting Uncle Xavier's garden. Richard's mother is visiting Uncle Xavier's garden. So Q is microwaves. and the order of microwaves is approximately 10 power negative 2. We have already seen such a question. For visible light, it is about 10 power negative 7. This side, 7 times 10 power negative 7. Infrared is 10 power negative 5, 10 power negative 6. Then the other side, we have ultraviolet, 4 times 10 power negative 7 is for violet. Then ultra must be less than ultraviolet. P and Q are fixed points at the end of a string. A transverse stationary wave of constant maximum amplitude is formed on the string. P and P, R, and Q are the only points on the string where nodes are formed. P, R, and Q. So there's a node here, there's a node here, there's a node there. Of course, in between every nodes, there must be an antinode. S and T are 2 points on the string at a distance x from R. So if this is a node, I could draw a wave here. I could draw something like that. So it means S and T are in uh, two adjacent loops, and it is a stationary wave. That means in most cases, S and T are vibrating 180 degrees out of phase. What is the relationship between points S and T? The same amplitude and in phase. It may not be the same. Different, actually, the amplitude for S is less than that for T because S is further from equilibrium. Okay, the amplitudes could be very close, but not the same because particles vibrate with different amplitudes. Then, different amplitudes and in phase. They are actually not in phase. The same amplitude, the amplitude is the same, and a phase difference of 180, the answer is C. The amplitudes are the same, but they are not in phase. Two identical loudspeakers are connected in series to an AC supply as shown. Let's look at this diagram. The microphone is moved along the line PQ. Which graph best shows the variation with the distance from P of the intensity of the sound detected by the microphone? The microphone are identical and are connected to the same signal generator. That means they are coherent sources. The intensity of these must be the same, of course. That means this one is wrong because the intensity must be must be highest at the center because there's a point where that is going to be like the zeroth order. That's where the intensity is maximum, and then it goes on decreasing on both sides of the maximum. So here we have intensity is maximum, but then it remains constant on both sides. That's wrong. Here the intensity is the same all through. That's wrong. Here it is the same all through. That's wrong. So the intensity must be maximum at the zero order. Then it goes on decreasing as we move away from the center. So the answer is going to be A. A diffraction grating experiment is set up using orange light of wavelength 600 nanometers. The grating has a slit separation of 2 times 10 power, 200 micrometers as shown here. What is the angular separation θ2 minus θ1 between the first and the second order maxima of the orange light? Okay, so we know that n lambda for diffraction grating is equal to d sine theta. So for the first order, n is 1, wavelength is lambda, d is the same, and then sine theta, theta is θ1. So that means θ1 is going to be lambda sine inverse of lambda divided by d. Then θ2, let me first wait doing that because I may need to divide. Then for the second one, n is 2 times lambda, the wavelength is lambda, then equals to d sine of theta 2. So we divide the two equations. So we have that, or we can substitute the first equation into the, what is the angular separation between the first and the second order maxima? Oh, d was given. Why am I suffering? D is given. So for the first one, theta 1 is going to be lambda, which is 600 nanometers, that is times 10 power negative 9, divided by d, which is 2 times 10 power negative 6, then sine inverse. So 600 exponent negative 9 divided by 2 exponent negative 6. So sign of the answer, no. (600) exponent negative 9 divided by 2 exponent negative 6. Then I also shift sine inverse of the answer, which is 17.5. Then I'll check the second one. Theta 2 is equal to sine inverse of, I'm substituting this equation, n is going to be 2. So that will be 2 times 600 times 10 power negative 19 divided by 2 times 10 power negative 6. So 2 times 600 exponent negative 9 divided by 2 exponent negative 6. Then shift sine inverse of the answer. So that is 36.9. So we want the difference. 36.9 minus 17.5. So that is 19.4. So the answer is going to be B. So the difference is 19.4 when you subtract 36.9 minus 17.5. That is 19.4 degrees. A whale produces sound waves of frequency 5 Hz. The waves are detected by a microphone and displayed on a CRO, on an oscilloscope, as we can see. What is the time-based setting on the oscilloscope? So you see that the length representing one cycle is 2 divisions. So period is equal to the time-based setting times, the length of one cycle times the time-based setting. The period is 1 over f, which is 1 over 5. This is equal to the length, which is 2 divisions, because they have given this in terms of divisions. 2 divisions times x. So, and it is in milliseconds. So it is going to be 1 over 5. Then times 2, I'm dividing by 2 divisions. This is going to be x. Remember, this was in seconds. Then, so our answer is going to be 1 divided by 10, which is 0.1 seconds per division, 0.1 seconds per division equals to x. Then we have to change this to milliseconds, so that will be divided by 1 exponent negative 3, which is going to be 100 divisions per second. So this is equal to 100 milliseconds per division. That is equal to x. So the answer is going to be D. A transverse wave in a medium has the waveform shown here, where y equals to the vertical displacement and x is the horizontal distance. The speed is 20 centimeters per second. The particle of the medium oscillates vertically. Which graph of vertical displacement against time best represents the motion of the particle? Okay. So since the speed is 20 meters per second, and we are seeing the wavelength as 4 meters per second. We could find a period. Let's find a period. So V is equal to lambda F. V is equal to lambda times F, which is equal to lambda time over T. So it means the period is going to be lambda divided by V. So the wavelength is given as 4 centimeters. Yes, the wavelength is 4 centimeters and the speed is 20 centimeters per second. That means the answer is 4 divided by 20, which is 0.2 seconds. So the period is 0.2 seconds. So let's check. This one is showing 0.2 seconds. This is showing 4 seconds. This one is showing 8 seconds. This is showing 10. So the answer is strictly A. The graph shows the variation of the displacement of particles with distance along a transverse wave at an instant in the time. The wave is moving to the right. So the wave is moving in this direction. That means the distance is increasing the other side. Which position along the wave corresponds to a point where the particles in the wave are traveling the fastest upwards? They are traveling the fastest upwards. First of all, particles here are traveling, they are vibrating downwards. A particle here is at rest, at rest, at rest. So here the particles are at rest. Particles have maximum speed when they are passing through equilibrium. But note that the wave is moving towards the right. So it is moving from the left to the right. That means the particle here, the particle at this point here, first of all, fastest upwards. The particle here is vibrating upwards, the particle here is vibrating downwards. So the answer is going to be A. Particles at C are vibrating fastest but downwards, particles at A are vibrating fastest but upwards. A long tube filled with water has a tap fitted at its base, as shown in the figure here. A tuning fork is sounded above the tube and the water is allowed to run gradually out of the tube. A loud sound is heard at intervals as the water runs out of the tube. The change in water level between louder sounds is 32. So the distance between successive resonance points is equal to 32 centimeters, and this distance is always this distance is going to be half wavelength. What is the wavelength of the sound? What is the wavelength of the sound? So this is very simple. So wavelength is going to be 2 times 32, which is equal to 64 centimeters. So the answer is going to be C. The distance between two successive resonance points is half wavelength, and the loud sound is heard at resonance points. A stationary insect on the surface of water creates circular waves with its legs, as shown in the figure here. The insect begins to travel to the right, as shown in the figure here. Okay. Which law describes the change to the waves at x caused by the movement of the insect? The wavelength is decreasing, the frequency increases, as we can see. The wavelength is decreasing, but the frequency is increasing. The speed must remain the same. So the answer is going to be D. The frequency decreases, not at all. Frequency decreases, not at all. The frequency increases, but the wave speed cannot increase when the frequency increases. V is equal to lambda times F. The frequency has increased, but we are seeing from the diagram that the wavelength has decreased. That means the speed must stay the same. A toy motorboat moving with a constant velocity vibrates. V vibrates up and down on the surface of a pond. This causes the boat to act as a source of circular water waves of frequency 2 Hz. The speed of the waves is 1.5 meters per second. A man standing at the edge of the pond observes that the waves from the boat approach him with a frequency of 3.0 volts. The formula for Doppler effect calculations with sound waves may also be used for water waves. What is the possible value of V? This causes the ball to act as a source of waves. What our frequencies is that the observed frequency is higher, so F naught is equal to the speed. The speed of the waves is 1.5 divided by this divide by 1.5. Because it's moving towards, this is going to be minus V, which is the speed of the source, then times the natural frequency of the waves, which is 2.0. They gave us F naught as 3, so we shall say this will be 3 divided by 2.0 is equal to 1.5 divided by 1.5 minus V. So I'm just solving this. 3 times 1.5, that is 4.5. Yes, 4.5 minus 3 is equal to 3. Minus 3V is equal to 3. So it means I'm making V the subject. So V is going to be 1.5 divided by 3. I've just collected like terms. So 1.5 divided by 3, which gives me a half, that is 0.5. So V is equal to 0.5 meters per second. So I ignore C and D. Then direction, because the frequency is higher, it must be towards. It must be towards the man. So the answer is going to be B. Two progressive waves of frequency 300 Hz superpose to produce a stationary wave in which adjacent nodes are 1.5 meters apart. What is the speed of the progressive wave? So we want speed. V is equal to, they said adjacent nodes are 1.5 meters apart. So distance between two adjacent nodes is equal to half wavelength. So which means the wavelength is going to be 2 times 1.5, which is 3 meters. So speed is going to be 3 times 300, because it is lambda f. V is equal to lambda times f. 3 times 300, which gives us 900. So the answer is D. A double slit interference experiment is set up as shown in the figure here. Fringes are formed on the screen. The distance between successive bright fringes is found to be 4 millimeters. So this is going to be X. Two changes are then made to the experimental arrangement. The double slit is replaced by another double slit which has half the spacing. So spacing is changing. So we have A, or lambda, is equal to AX over D. Initially, we are using the same light. The screen is moved so that the distance, its distance from the double slit is twice as great. The light has remained the same. So here the wavelength has remained the same. The slit separation is 4. No, the slit separation, let's say it is A, and the fringe separation is 4 millimeters. The distance is D. For the second one, the wavelength has remained the same. Two changes are then made to the experimental arrangement. The double slit is replaced by another double slit which has half the spacing. Has half the spacing. So where there is A, I'm putting a half A. Then it means X must change. I will call this one X2. Half the spacing. The screen is moved so that its distance from the double slit is twice as great. So D is going to be twice as great. What is now the distance between successive bright fringes? What is the value of X2? That is very easy. Lambda is equal to A times 4 over D. I will just substitute for lambda in this second equation. So I will say A times 4 over D is equal to a half A X2 over twice D. So A cancels, D cancels. So this becomes a quarter. This becomes a quarter times, so it is 4 equals to 1 over 4 times X2. which makes x2 to be equal to 16. So x2 is going to be 16 millimeters, so our answer here is going to be 16. The interference patterns from a diffraction grating and a double slit are compared. Use the diffraction grating, yellow light of the first order is seen using the diffraction grating, yellow light of the first order, so small n is equal to 1, is seen at an angle at theta degrees to the normal to the grating. Okay. The same light produces so theta is 30. The same light produces interference fringes on the screen 1 meter from the double slit. The slit separation is 500 times greater than the line spacing of the grating. What is the fringe separation on the screen? So for diffraction grating, we know that n lambda is equal to d sine theta. The interference patterns from a diffraction grating and a double slit are compared. For a double slit, we have that lambda is equal to ax divided by d. Using the diffraction grating, yellow light of the first order, so n is equal to 1, is seen at an angle at an angle is seen at 30 degrees to the normal to the grating, so theta is 30. The same light produces interference fringes from the double slit. So wavelength is the same. Then this is going to be d. D for the diffraction grating, sine of 30. That is for the diffraction grating. Then for the double slit, the wavelength is still lambda. The same light produces interference fringes on a screen 1 meter. So D, capital D, is 1 meter. The slit separation of 500 times. So A, the slit separation is 500 times greater than the line spacing of the grating. The slit separation is A. A is 500 times greater than the line spacing, which is X, which is D. A is 500 times D. So where there is A in the diffraction grating, I'm going to just put there 500 times D, then times X. So what is the fringe separation on the screen? So we want the fringe separation on the screen. So I'm just going to combine these two equations. So where there is lambda, I will put there D sine 30. So I'll say D sine 30 is equal to 500 times D over 1 meter. 1 meter is going to be useless, then times X. So this one cancels. Sine 30 is a half. So X is going to be equal to sine 30 divided by 500, which is going to be 1.0 times 10 power negative 3. So X is going to be 1.0 times 10 power negative 3 in meters. So the answer is going to be C. The diagram illustrates the position of particles in a progressive sound wave at one instant in time. So P, the particles are close. Q, they are further apart. Again, they become close. So the distance between this is going to be like a compression and a rarefaction. That is half wavelength. Distance between a compression and a rarefaction, that's half wavelength. So L is corresponding to half wavelength. The speed of the wave is v. P and Q are 2 points in the wave a distance L apart. What is an expression for the frequency of the wave? So here it means lambda is equal to twice L. Frequency is equal to V over lambda, which is V over twice L. So it means here the answer is going to be A. A wave moves along the surface of water. The diagram shows the variation of displacement S with the distance along the wave at time t equals to 0. Which graph best shows the variation with the time t of the displacement S of the point P on the wave? So the wave moves along the surface of water. The diagram shows the variation of displacement S with distance along the wave at time t equals to 0. So it is showing displacement. Which graph best shows the variation with the time t of the displacement S of the particle? Displacement S of the particle. Since at time t the particle is already here, it means our graph should not start from the origin. That means we shall eliminate all graphs starting from 0, 0. This one is eliminated. And which one else? A. So we have eliminated B. Secondly, if we consider the upper part displacement to be positive, it means all graphs starting from the bottom will also be neglected. So we look for graph starting here at t equals 0, displacement is in the opposite direction, so that one we shall also neglect it. So we remain with D and A. We have remained with D and A. Now we expect that after a small time the displacement should go to 0. But here the particle is vibrating and the particle it is actually moving downwards, so it will not have changed direction. Here the particle was vibrating, actually here the particle is vibrating upwards, so it must not have changed direction at this point here. Therefore it means for this first part here the particle must be vibrating in the same direction. Therefore it means we have also ignored this one, because this one shows that the displacement of the particle has changed direction. This one shows that the displacement of the particle has not changed direction, not until it reaches the other end. So the answer is going to, sorry, this one here, the displacement has not changed direction. So it means the answer is going to be D, because here the particle is vibrating upwards. The particle is vibrating upwards. So it reaches at this point, at this end, the particle is vibrating upwards and the speed becomes 0 at this point here. It does not become 0 here. Therefore, this disqualified A, and it means our answer is going to be D. In an experiment to determine the wavelength of sound in air, a stationary wave is set up in an air column. The distance between a node and an adjacent antinode, that is a quarter. Distance between a node and an adjacent antinode is a quarter wavelength. Think about a node and an antinode here. Node, antinode, this is a quarter of a cycle, so it is a quarter wavelength. What's the wavelength? Of course, the wavelength is going to simply be 4 times L. So this will be 4L. In one of the first experiments to demonstrate the Doppler effect, a train was filled with trumpeters, all playing a note of frequency for 40 Hz. The difference in observed frequency of the note as the train directly approaches the stationary observer was 22 Hz. The speed of sound was 340. At which speed was the train moving? So the difference in the observed frequency of the note as the train approaches a stationary observer. So the observer was stationary, the normal frequency is 440. So if it approaches an observer, the observed frequency F naught is equal to V, which is 340, divided by 340. This is going to be minus the speed of the train, Vs. This is times 440. But they have told us that Fs minus F naught is 22. Fs minus F naught is 22. That means the observed frequency is going to be 440 plus 22. So 440 plus 22 is going to be equal to 340 times 340, 440 divided by 340 minus V of the source. So this is going to be I'm just going to get 340 times 440. Then I will divide this by the sum of the two, 440 plus 22. So I have that 340 minus Vs is equal to 323.8. 323.8. So it means Vs is going to be, I'm making Vs the subject here, so I'll just subtract. So 340 minus the answer, which is equal to 16.2. So that is 16.2 meters per second, making the answer to be B. The electromagnetic spectrum consists of waves with different wavelengths. Which row correctly identifies regions of the electromagnetic spectrum? So wavelength of 10 power negative 10 can never be microwaves. Makes that one wrong. It can never be microwaves. This is wrong. So we have eliminated A and B. Then the wavelength of 10 power negative 2 can never be for, of course, it can never be for X-rays. It can't be for infrared. It can't be for ultraviolet. So our answer is D. A cathode ray oscilloscope is used to display the trace from a sound wave. Note carefully how I quote these waves. I always look at Rubenera's mother is visiting Uncle Xavier's garden. I use this as the reference, which is 7 times 10 power negative 7 meters up to 4 times 10 power negative 7 meters for visible range. This is violet, this is red. So it means we have eliminated 10 power negative 10 for microwaves and for X-rays because they can't be, they are on the other side. So the power of 10 must be bigger or a small negative number. But then now we have the extreme end, I have 10 power negative 2. 10 power negative 2 is microwaves, it can't be infrared. That's why straight away went to D. A cathode ray oscilloscope is used to display the trace from a sound wave. The time base is set at 5 microseconds per millimeter. What is the frequency of the sound wave? So here we can see one cycle. It is very hard to estimate one cycle here, but we are going to try. Okay, we can estimate. We are just going to use an estimate. Let's think that one cycle stops here. Maybe this is a repeat of the second cycle. So this is 1, 2, 3. So one cycle is 3 centimeters. Okay. Frequency is equal to 1 over period, which is equal to 1 over the length representing one cycle times the time base setting x. So this is 1 over the length representing one cycle is approximately 3 centimeters. And the time base setting is in millimeters. So I have to change this to millimeters. So I will divide this by 10 to change it to millimeters. So it is 3 millimeters times 5 times 10 power negative 6. So it is now in seconds per millimeter. Seconds per millimeter. So per millimeter is cancelled already. So now I have this as 1 divided by 0.3 times 5 exponent negative 6, which is 6.7 or 67. This is 3. No, this is supposed to be times, not divide by. With converting from centimeters to millimeters, I should divide, I should not divide, I should multiply. So 3 centimeters to millimeters, it is the same as 30 millimeters. So this would be 30 millimeters. So millimeters cancels. So it is 1 divided by 30 times 5 exponent negative 6, which is 6.7 kilo, 6.7 kilonewtons, 6700 hertz. That is 6.7 kilohertz. So the answer is going to be automatically C, approximately C. Monochromatic light is directed at a diffraction grating as shown here. Which diagram could show all the possible directions of the light after passing through the grating that give maximum intensity? Automatically A is going to be wrong because every time there is light incident on a grating, it means there is a maximum intensity in the same direction as the light. Here it is showing there is no maximum intensity in the same direction as the incident light. That one is out. This one is also going to be out because there must always be a maximum intensity, or a maximum intensity can also be observed at different angles. So there are different orders. This one is showing there are just there's only one order on both sides of the intensity maximum in the same direction as the incident light. There must be different orders. So this one is also out. So we remain with B and C. So now here what is going to change, what is going to make an answer to be correct is going to be the angle between the diffraction maximum or measured from the central maximum. Remember, for a diffraction grating, n lambda is equal to d sine theta, which means the theta is the sine inverse of n times lambda over d. If we assume that n is equal to 1, then theta is going to be sine inverse of lambda over d. And if n is equal to 2 or n equals to 3, it means theta is going to be actually the second for the second order, or for the further orders, the value of theta is going to be greater. But then when I subtract the next order minus the previous order, the difference in that angle is going to always be greater than the difference in the angle of the first order. So if I find the theta here as theta 1, and I try to find theta 2, note that theta 2 minus theta 1, because of this, the sign here, theta 2 minus theta 1 is always going to be greater than theta 1 itself. Yet here it is showing that theta 2 minus theta 1, which is this angle here, theta 2 minus theta 1 is less than theta 1, which is practically not possible. In fact, if we get theta 3 minus maybe theta 2, it should also be greater than actually theta 2 itself, or it should be greater than theta 2 minus theta 1. Therefore, this angle here, it goes on actually becoming bigger and bigger. Therefore, it means the answer is going to be C rather than this one, because this one is showing that the angle is actually becoming smaller. Okay, so that is going to be C. Why can unobservable interference pattern never be obtained between two monochromatic beams of light from different lamps? Even though they are monochromatic, it is impossible to have two coherent sources which are independent. It is practically not very, very possible. So number one, the frequency of the light from the two lamps can never be the same. It can be the same. The light from the two lamps can never be coherent. That is one of the most appropriate answers. The light from the two sources can never be coherent, so that is going to be true. The phase changes abruptly, so they can never be coherent. They cannot maintain a constant phase difference all throughout. A student sets up apparatus to observe the double slit interference of monochromatic light as shown here. Interference fringes are formed on the screen, which change would increase the distance between adjacent fringes. So since it is a double slit, lambda is equal to AX divided by D. We want X to increase. X will only increase when wavelength increases or D increases because they are directly proportional. X will also increase when A decreases because they are inversely proportional. So decrease the distance between the two slits, that one decreases X. Decrease the width of the slit separation because they are inversely proportional, it increases. So the answer is going to be B. Decrease the distance between the two slits. Sorry, the answer is A. Decrease the distance between the two slits, that is A. A has been decreased. The distance, decrease the width of the slits, that one just affects the intensity. Decrease the distance between the two slits, that is A, not D. When D is decreased, X decreases, but the distance between the slits is A. So it decreasing because A is inversely proportional to X. If A decreases, X increases. Okay. The graph shows the variation of the displacement y with the distance x along the progressive wave at one instant in time. What is the phase difference between points P and Q? So point P is at rest. Point Q is also at rest because they have reached maximum displacement. But then, before reaching point P, the particles here were actually vibrating upwards, and particles here were actually vibrating downwards. That means P and Q are most likely going to be either 180, they are actually in antiphase, or we look for any angle which is related to antiphase. Therefore, they can't be 90 degrees, they can't be 270, but it can be 360 plus 180, 360 plus antiphase, which is 180. So that is giving us, let's check, 360 plus 180, which is 550. So the phase difference is going to be 540 degrees. That is still antiphase. Alternatively, you can look at this as P is here and Q is here. Let's see the distance out of step in terms of wavelength. Let the wavelength be lambda. In terms of wavelength, this is going to be lambda. This is a quarter lambda and a quarter lambda. So wavelength plus a half wavelength. That is the distance out of step, which is going to be 3 lambda over 2. So the phase difference is going to be 360 into 3 lambda over 2 divided by lambda. Lambda cancels. So you have 360 times 3 over 2, which is 360 times 3 divided by 2, which is 540. Wave power generators take advantage of the energy that is transferred by the motion of waves across the surface of the oceans. The energy of a wave depends on its amplitude. What is the correct definition of amplitude? That one is maximum displacement of a point from equilibrium position. Maximum displacement from equilibrium position, that is C. The sound wave of frequency 270 Hz is recorded by a cathode ray oscilloscope. The waveform on the CRO is shown here. What is the time-based setting on the CRO? So we know that frequency is equal to 1 over period, or 1 over period is, frequency is 1 over period. And this is going to be, the frequency is, or the period is equal to 1 over frequency, which is equal to 1 over 270. But the period is equal to the length of one cycle times the time-based setting. So we shall say 1 over 270 is equal to, the length representing one cycle is going to be, let me see how many cycles here. It's hard to find a very convenient point, but I'll find one. So this is, we cannot tell whether this is reaching here. So I'm just going to estimate between so this is 1, 2, 3, and approximately a half. So we shall just get an estimate 1, 2, 3, and a half. So those are approximately 3.5 centimeters. So let me just take 3.5 centimeters. So that is 3.5 centimeters times the time-based setting. Remember, this is in seconds. So x is going to be, because it's per centimeter, I'm making x the subject, so it will be 1 divided by 270 times 3.5. So that is 0.001. So x is equal to 0.001 seconds per centimeter, which is approximately, of course, there is 0.11, but this is approximately 1 millisecond per centimeter. So the answer is B. A motorboat vibrates in the water so that it produces water waves of frequency 0.2 Hz. The speed of these waves in the water is 20 meters per second. The motorboat moves with a speed of 5 meters per second, directed towards the stationary sailing boat. The Doppler effect equation for sound waves also applies to water waves. What is the frequency with which the waves hit the stationary sailing boat? Okay, so since the motorboat moves with that speed directed towards, so observed frequency is going to be the speed of the waves, which is 20 divided by 20. Because it is moving towards, we shall subtract. So it is minus the speed of the boat, which is 5, then times the frequency of the waves, which is 0.2. Because it is towards, the frequency must be above 0.2. That means I cannot even check this. I can't check that. So I check the rest of the two, the remaining two. So this will be 20 divided by 15 times 0.2, which gives me 0.26. Therefore, the answer is 26 recurring, which makes it to be 0.27. So the answer is D. Infrared laser light is used for the transmission of data along optic fibers. What is a typical wavelength of infrared? Rumenira's mother is visiting Uncle Xavier's garden. Infrared is after red, and red is 7 times 10 power negative 7. So this should be very close to 10 power negative 7. That means I can ignore this one, I can ignore this one. I remain with these two. This one is still in the visible range, so it can't be infrared. So the answer is most likely going to be the answer, because 5 times 10 power negative 7 is between 7 and 4 times 10 power negative 7. So the answer is most likely going to be A. An elastic string is attached to an oscillator at one end and clamped at the other end, so that the string is horizontal and in tension. The oscillator is made to oscillate vertically. The frequency of oscillation is gradually increased from 0 until a stationary wave is set up in the string. The frequency is then increased further to frequency f when a second stationary wave is set up in the string. The frequency is then increased further, at which frequency does a third stationary wave occur. It is a string, so frequency is equal to n times f naught, where n is going to be 1, 2, 3, 4. All harmonics are present. all harmonics are going to be present, and n, but they have said the second, when n is 2, so f is equal to twice f naught, which means f naught is equal to f divided by 2, which is going to be 0.5 times f. The fundamental is 0.5 times f. So at which frequency does a third stationary wave occur? So f should be n should be 3. So f3 is going to be 3 times f naught, which is going to be 0.5 f over, times 3. 0.5 times 3, that is 1.5. So the answer is B. May I use the simple method? Because for a string, all harmonics are present. That's why I used n. If n is equal to n, f naught, where n is the harmonic. N is the harmonic, and all harmonics are present for a string, which is like for an open pipe. That's why n is equal to 1, 2, 3, and so on and so forth. For the first, n is equal to 1. So f1 is equal to f naught. For the second, n is equal to 2. So f2 was given as f in this case, but n is 2. So f2, which is f, is twice f naught. So f naught is going to be f over 2. That's why I got 0.5 times f. So f3, which is the next, is going to be 3 times f naught, which is 0.5 f times 3. In an experiment, water waves in a ripple tank are incident on a gap, as shown. Some diffraction of the water waves is observed. Which change to the experiment would provide a better demonstration of diffraction? So we see that the wavelength is smaller than the gap. Increase the amplitude, not at all. Increase the frequency, that one decreases the wavelength further. Increase the wavelength of the wave. So if we increase the wavelength so that it is very close to the size of the gap, then we shall experience good diffraction. Light of wavelength lambda is emitted from 2-point sources R and S and falls onto a distant screen, not to scale. At point P on the screen, the light intensity is 0. What could explain the 0 intensity at P? If the light intensity is 0, there could have been the destructive interference. And if there was destructive interference, what could be the conditions for the destructive interference? Light from the two sources emitted 180 degrees out of phase, and the path difference at P is a half lambda. Light from the two sources is emitted 180 degrees out of phase, and if it is 180 degrees out of phase, then the path difference should be 0 for there to be an intensity maximum here. It should not be a half lambda. Light from the two sources is emitted in phase, and the path difference is lambda. That will be constructive interference, so the intensity can't be 0. By the way, this one is also constructive because if the phase difference, the path, the phase difference was 180 degrees out of phase, and yet the path difference is a half lambda. The path difference to P is a half lambda. It means there will be constructive interference because this is half a cycle ahead of each other, and then the path difference is half, so half plus a half is lambda, so that is constructive. Where we expect a minima, if the sources are 180 degrees out of phase and not 0, it becomes a maximum. Where we expect a maximum, if the sources are 180 degrees out of phase, then it will be a minima. Light from the two sources is emitted in phase and the path difference is lambda. That one is not possible. Light from the two sources is emitted 90 degrees out of phase. 90 degrees out of phase, and the path difference to P is lambda. 90 degrees out of phase, and the path difference is lambda, so 90 degrees is a quarter of a cycle, then plus lambda, that is 3. This will be 3, no, it will be 5 over 4 lambda. Then light from the two sources is emitted in phase, and the path difference to P is a half lambda. Light from the two sources is emitted in phase. That means the phase difference is 0, but the path difference to P is a half lambda. I think that is automatically destructive interference. The most direct one is D. This one here may not cause total cancellation because of the phase difference being 90 degrees. So it may cause destructive interference, but not zero intensity at point P. So the phase difference between the sources is 0, but the path difference is half lambda, which makes destructive interference to occur. Apparatus is arranged to show a double slit interference using monochromatic light. The slit separation is 0.1 millimeter. The distance from the double slit to the screen is 2.4 meters, and the fringe width is 12. So this is slit separation is A, this is capital D, this is X. What is the new? The distance to the screen is now changed to 1.8, and the slit separation is doubled. So let's come up with two equations. Lambda equals to AX over D. For the first, it is for the same light, I guess. So the first one, lambda is equal to A which is 0.1, I will not change any unit. Then X, which is 12, D, which is 2.4. Then for the second one, lambda is equal to A. The distance to the screen is now changed to 1.8 meters, and the slit separation is doubled. So A is twice. So this is 0.1 times 2, so it is 0.2. Then the fringe separation is not known, X. Then the distance is changed to 1.8. So I'm just going to equate the two equations. So I have 0.2x over 1.8 is equal to 0.1 times 12 over 2.4. So I just find x, 0.1 times 12 divided by 2.4 times 1.8 divided by 0.2. So I am getting 4.5 millimeters. So the answer is B. Monochromatic light of wavelength 690 nanometers passes through a diffraction grating with 300 lines per millimeter, producing a series of maxima bright spots on the screen. What is the greatest number of maxima that can be observed? Remember, there is a central bright maxima, then there is a maximum order this side and a maximum order the other side. So we add this value of n to this, to get the total. Okay, so the number of maxima, the maximum order is obtained when sine theta is equal to 1. So n lambda is equal to d sine of theta. The maximum value of n is going to be d. Remember, d is equal to 1 over n, and n should be in meters, in per meter. So this is 1 over 300 times 1000 to change it from per millimeter to per meter. So this is going to be, d is going to be 1 over 300,000. Sine theta is 1. Then times the wavelength, which is 690 times 10 power negative 9. 1 divided by 300,000 times 690 exponent negative 9. So that is 4.8. So we round off to 4. It is 4.8, but we round off to 4, not to 5. Not to 5. So this is going to be 4 that side, plus the central, which gives us 9. So it is 4 plus 1 plus 4, which gives us 9. We do not round off to 5, not to 5. A transverse wave is moving along a rope. 2 points x and y on the rope are a quarter of wavelength apart. Which statement is not possible for the 2 points x and y? 2 points x and y on the rope are a quarter wavelength apart. Which statement is not possible for the 2 points x and y at any instant? It is a transverse wave which is moving along a rope. Okay, So they are both stationary. That is not possible. That is not possible for both because it is a transverse wave is moving along a rope. 2 points x and y on the rope are a quarter of a wavelength apart from each other. Okay, if they are quarter a wavelength, then we have to think about this answer again. Which statement is not possible for the 2 points x and y at any instant? They are both stationary. They are a quarter, they cannot be stationary. They are displaced in opposite directions from their equilibrium. That one is possible. If you look at 2 points a quarter distance apart, it is possible for them to be displaced in opposite directions. They can be moving in opposite directions. They both have displacements of the same magnitude from the equilibrium position. Of course, for transverse waves or for longitudinal waves, as long as the wave is progressive, they have the same displacements. The displacement will be of the same magnitude from their equilibrium positions. Because they are a quarter wavelength apart, so they will have the same displacement from their equilibrium positions, but they cannot both be stationary. They're actually vibrating. Two progressive waves meet at a fixed point P. The variation with the time t of the displacement of each wave at point P is shown in the figure here. So this is the last equation for part 2. What is the phase difference between the two waves at point P? So we can find let's look for corresponding points. Let's look for corresponding points. For this wave here, if I take this part here, its corresponding part is going to be this one here, approximately. So the time out of step is going to be 0.7 minus 0.2, which is equal to 0.5. That is approximately the time out of step. So phase difference is going to be 360 into the time out of step, which is 0.5 divided by the period. So the period is actually going to be 0.8. So I'm going to get an estimate value, 0.5 divided by 0.8. 0.5 divided by 0.8 times 360. So that is 225. So I have 360 minus the answer, which is 135. So the answer here is going to be 135. Alternatively, you can check. I've just got 360 minus what I've just got here, because we'll be having the same effect, which is 225, and that gives me 135. Alternatively, you could look at let me check. I will look at 0.1 and 0.4 for the other wave. So the time out of step here is going to be 0.4 minus 0.1, which is 0.3. So it means the phase is going to be 360 at 0.3 divided by the period. The period is 0.8. So divided by 0.8. So this is going to be 0.3 divided by 0.8 times 360, which is 135. So this could be 135. So this is the most easiest one. Look at corresponding points and find a time out of step. So the most appropriate is going to be this one here, 135 degrees direct. Okay, that's the end of part 2. See you in part 3, and bye bye.